With the ramifications of incompressibility now in hand, we can turn to the effect that forces have on the ether. The first force we will consider is the force of tension. Here we see 3 cubes of ether, as well as the tension forces that act on the central cube. Please note that, of course, in the real ether, the cubes will have adjoining faces, and that I have separated them out here in an effort to make the drawing clear. It is known that tension forces in a solid lead to transversely polarized waves, with a familiar example being waves on a string. Since light is also known to be a transversely polarized wave, it is natural to assume that the ether is a solid under tension. Note from the diagram that the longitudinal force will typically cancel out, as the longitudinal component of T sub 2 is almost exactly opposite to the longitudinal component of T sub 1. This leads to the observation that it is the transverse components of the tension that are responsible for the forces which cause the wave motion within the solid. Here we will delve a bit deeper into the analysis of tension. The tension force will be directed from the center of one cube toward the center of an adjacent cube, and so we must recall where these cube centers are. Recall from our setup of the analysis that we have defined the vector p to be the relative position of the positive ether with respect to its undisturbed equilibrium position. Hence, the cube originally centered at R is displaced to R plus P, where P is evaluated at R, while the cube that's originally centered at R prime, which is delta x times I away from the cube at R, that cube at R prime is displaced to R prime plus P evaluated at R prime. And hence the force direction, which we'll call capital D, is equal to the position of the cube, the adjacent cube, which is R prime plus P evaluated at R prime, minus the position of the cube, the original cube, which is R plus P evaluated at R. And we subtract the position of the center cube from the position of the cube on the right. Making this subtraction, we realize that R prime minus R is simply delta x times I, and then we bring down P evaluated at R prime minus P evaluated at R. That's the direction of the force. If we now assume that the oscillations within the ether are small, that would say that the change in P over the distance delta x is much less than 1. We can now assign a new vector, small d, which is the limit of big D as delta x becomes small. We're going to divide big D by that small value of delta x to arrive at the little d value. That will be a vector in the direction of the tension. Performing the division, we just take delta x and divide it through, and we get I from the first term. And then we recognize that as delta x goes to 0, that p of x plus delta x, y, z, and t, minus p of x, y, z, and t, all divided by delta x, in the limit as delta x goes to 0, that's the definition of the partial derivative of p with respect to x. We can then expand the partial derivative of p with respect to x into its Cartesian coordinates, or components. So we've got the partial p sub x with respect to x, plus partial p sub y with respect to x, partial p sub z with respect to x, all associated with their own unit vectors. And now we want to take the magnitude of this vector by squaring the components and taking the square root. Keeping terms only first order in small quantities, we'll take this, the squared terms will go away because they're small terms squared. But the leading term here will give us 1 plus 2 partial p sub x partial x plus partial p sub x partial x squared. We'll take that leading term, and then when you take the square root of 1 plus epsilon to the n, you get 1 plus n epsilon. So that allows this expression here to be replaced by 1 plus partial piece of x with respect to x. Now a unit vector in the direction of the tension will be given by a vector in the direction of the tension divided by its magnitude. Well, the vector d we've seen is expressed here, and then we're going to divide by the magnitude of d to get the final expression on this page. So a unit vector in the direction of d, in the direction of the tension, will simply be the unit vector I plus the partial of y with respect to x times the unit vector j plus the partial of p sub z with respect to x times the unit vector k. Note that this doesn't exactly look like a unit vector because I itself is a unit vector, so this would be a bit larger. But to first order in small quantities, this is the unit vector in the direction of the tension. With the unit vector for the tension just derived, we can express the tension force as T times U, where T is the magnitude of the tension and U is the unit vector that we've just derived. We can expand that unit vector in the form that we just saw on the previous slide. Now the tension on the right YZ face of the cube will be the tension evaluated at x plus delta x, y, z, and t. And that'll be the magnitude of the tension at that point multiplied by the unit vector at that point. On the left xy face, we'll have the magnitude of the tension evaluated at x, y, z, and t. And we also notice that on the left yz face, the tension points in the opposite direction, so we have a minus sign that's introduced. We then have the unit vector evaluated at the left yz face. Now the force on a side of the cube will be equal to the tension per unit area multiplied by the area of the side. Since we've got a constant tension on the side of the cube, the larger the area, the more force there's going to be on a given cube. So therefore, the total force on the cube is given by the area of the YZ face of the cube times the sum of the tension forces that are existing on the cube. We can now take this expression and multiply and divide it by delta x, and then we can form the expression as we let delta x go to 0. If we look at the x component of the force, as delta x goes to 0, we'll have the magnitude is t of x plus delta x, y, z, and t, minus t of x, y, z, and t. That's our x component of the force because you can see it multiplies the unit vector I. If we now divide by delta x, we recognize this quantity as being the partial derivative of the magnitude of the tension with respect to x. Now, for the y component of the force, the tension force, we'll notice that the tension at x plus delta x is going to be approximately equal to the tension at x, and we'll call that tension T0. And to first order in small quantities, those two things will be the same. So we'll have this T0 times the partial of y, p sub y evaluated at delta x plus delta x minus T sub 0, the partial of p sub y evaluated at x, both of which are also evaluated at y, z, and t. And we can see that when we divide that by delta x, we'll get the second derivative of p sub y with respect to x times j. So this is the term that's first order in small quantities for the force in the y direction. Performing an identical analysis on the force in the z direction gives us that term as well. The result from the previous slide appears at the top here, where we have just evaluated the force due to the tension on the YZ faces of the cube as being given by this expression shown here. What remains to be done is to expand the term partial of t with respect to x. Now, from our original tension force law, remember that we postulated that the tension would increase linearly with the amount that a cube was stretched in the direction perpendicular to its faces. If it's not stretched at all, then that means that P is everywhere 0. P is our vector that says how much the position of the ether has moved with respect to its equilibrium position. And if it hasn't moved at all, then P is everywhere 0. In that case, the length of this cube is its original length, which is delta x. That then gives us the ability to evaluate the condition of the tension that normally exists in the ether without any disturbances as being K1 times delta x. Now, arbitrarily, the magnitude of the tension is K1 times the length of the cube, which is delta x, which is its undisturbed length, plus whatever displacement it has in the x dimension on the right face, minus whatever displacement it has on the left face in the x direction. That's given by this expression here. We can now replace K1 by T0 over delta x, and once again recognize that delta x divided by delta x is 1, and P of x evaluated at x plus delta x minus P of x evaluated at x, with y, z, and t going along for the ride, is again the partial derivative of P sub x with respect to x. This then says that if we now take the partial of t with respect to x, the partial of 1, the constant with respect to x is 0, and we get t sub 0, the second derivative of P sub x with respect to x. And therefore, plugging this result into the equation that we achieved on the previous slide gives us the final force equation for the tension that exists on cubes on the y, z faces as T0 times delta x, delta y, delta z plus a sum of the second derivatives with respect to x of P sub x, P sub y, and P sub z in the direction of P sub x, P sub y, and P sub z. We have just derived the tension force on a small cube of ether that results from the tension forces that are present on the YZ faces of the cube. That result is shown here. By doing exactly the same derivation for the XY and XZ faces, we will arrive at analogous expressions for the forces in those directions. As can be seen, the only thing that changes is that the partial derivatives are evaluated with respect to y and z instead of x. If we now sum these three force components, we will get the total force expression, and recalling that P is just the sum of its components, and that the Laplacian operator is just the sum of second partial derivatives, the equation for the tension force can be expressed in a very simple equation shown here as equation 5. I've highlighted this equation with red boxes as it will be used again later in this webinar.